Hi, today I'm going to describe the 3 CNF SAT to subsystem reduction. So I'm going to keep things a little informal and give intuition rather than formal proofs. Because I believe that after some time you don't remember the formal proofs or anything, but you can always carry the intuition with you. So let us get started. Before we do that, let me try to revise some of the key concepts for you. Okay. So I'll start with asking what uh, what do you understand by problems in P? So they are the problems which can be solved in polynomial time. For example, a DFS. Uh, a DFS traversal on a tree will take O of v plus e time, and this is polynomial in this is linear in the size of the tree, and linear is a perfectly well polynomial. So. Uh, so this is what I mean by polynomial algorithms. So now the next question is, what is NP? So NP are those problems which can be whose probable solution, and that is called a witness or a certificate, can be verified in polynomial time. Uh, for example, let's say you have a set of numbers and then you have a target value. And if I say that, um, does this set subset S dash add to T? Yes or no? So you can answer this question in polynomial time. You can just sum these things up and tell me if it adds to T or not. Uh, so when we talk about PNP or other things like NP complete, and we generally talk in terms of the decision problems only. This is simply to make your life easy and the analysis easy. Okay, so the next comes NP complete. So what the hell are NP complete problems? And so the first condition is they should be NP. They should be NP. That means if I give you a model probable solution, you can verify that solution in polynomial time. Okay, but apart from that, they have another condition. Okay, and before diving in that condition, we should understand what a reduction is. Okay, so let us see what a reduction is. So reduction is not something very new. So we have already seen reduction so many times. Let me give you an example. If I say that computing the median reduces to sorting, that means if you know an algorithm, if you know an algorithm for sorting, can you use that to compute your median? I think the answer is yes, because you can simply take the sorting algorithm and sort your array and output the middle term. That means if you know the algorithm for sorting, that can help you to compute the median. So median is nothing but sorting in disguise. Okay, so computing the median can be reduced to sorting. Likewise, if I say that detecting a cycle reduces to DFS, because if you know the algorithm for DFS, you can modify that to detect a cycle for you. Okay. Similarly, I can say that all pair shortest paths algorithm reduce to single shortest path algorithm, and that is true because if you know the algorithm for single shortest path, you can run it at all the nodes. You can run it at all the nodes, and that can essentially solve the all pair shortest path problem for you. Okay, so we have seen reductions, and we have done reductions in our head. So if you are thrown a problem, then you try to reduce it to a known problem in your head and solve it. You try to find the pattern and recognize already solved problem. So we have been doing reductions in our head. So why are reductions important now? Okay, so uh, before that, let me make a statement. So if I say that x is reduced to y, I can say that y is at least as hard as x. I cannot make the other way around statement, because you can imagine that you know x makes these portions of y. Okay, but there are still other instances of y which might not be derived from x. That means, at least these portions, we don't know anything about these portions, so we can only say that the portions of y which are kind of equivalent of x, they are at least as hard as x. Okay, but y has more things, so y can be like more hard, so we can only make a statement that y is at least as hard as x. Okay, so why we cared about reduction is because let's say if you pick up all the NP problems and assume that all those NP problems, let's say this is the set of all NP problems, and let's assume that all these NP problems reduce to one particular problem. Okay, so that problem is called as an NP complete problem. So a group of all the problems form the complete class called NP complete class. Okay, and if this reduction, if this reduction, uh, if this happens outside NP, then this problem are called NP hard. So that means everything in NP reduced to them, but they were not themselves NP. That means given a probable solution, you cannot verify that in polynomial time, and so that is NP hard. Okay, so loosely you can see that you have a NP class, and the polynomial lies inside the NP class because you can solve them in polynomial time. So verifying a solution is even easier, maybe. Okay, so if everything in NP reduces to these problems, and they're called NP complete. Okay, and if it reduces to a problem, if these problems they reduce to a problem, and those problem itself they don't lie in NP, then they become NP hard. Okay, and yeah, so now if I ask you to prove if a problem is NP complete, the first step is you'd prove that it's in NP, and you can do that by proving that you can verify the witness in polynomial time. Okay. The second step is you need to take every problem in an NP and reduce it to your problem. When I say this statement, this must have sounded insane. Like there are infinite many problems. You cannot convert everything to your problem. Okay, so it turns out you don't need to do that. Some people have found some known NP complete problems for you, and imagine that this is your already known NP complete problem, and that means everything reduces to them somehow. Okay, and now this was your problem sitting here. Okay, so if you manage to reduce your known NP complete problem to your problem, that means you're borrowing all these arrows and throwing them at your problem. That means your problem what can you say about the NP complete problems? You can say that these problems are the hardest problem in NP. Why so? Because everything in NP reduced to them. That means they are at least as hard as everything else is in NP. That means that makes them the hardest problems in NP. So if you reduced your known NP complete problem to your problem, that means you're claiming that your problem is at least as hard as the known NP complete problem. Okay, and that makes it the hardest problem in the NP class, and that makes it an NP complete problem. So you don't need to reduce everything in NP to your problem. You can pick a known NP complete problem and reduce it to your problem, and that does the job for you. Okay. So we now know about reduction and how to prove things are NP complete. Okay. Let us try to now prove that subset sum is NP complete. Okay. Let me briefly tell you what the subset sum is, and we will use a known NP complete problem called the 3 CNF SAT and reduce the 3 CNF SAT to subset sum. Remember, all the arrows came to this, all the reductions came to this, so we want to borrow all those reductions. So if you reduce the other way around, it won't mean anything. So we want to pick up our known NP complete problem, the 3 CNF SAT, and reduce it to the subset sum problem. So before that, let us revise the subset sum problem, the 3 CNF SAT problem. So the subset sum problem says this. Yeah, you're given a set and a target value, and the decision problem is is there a subset S dash that adds to T? So this is the subset sum problem. Okay, so you can clearly see that this is an NP, because if I give you a subset, let's say 9 in 3, so you can easily verify in linear time that this adds to 12 or not. In this case, it's a yes. Okay, so we can say that subset sum problem is at least NP. Now we will reduce the 3 CNF SAT to the subset sum problem and claim that subset sum problem is also NP complete. Okay, and now let us see what the 3 CNF SAT problem is. Okay, so it's a Boolean expression, and it has literals like x1, x1 bar, x2 bar, and these things. So these literals can take the value of true or false, or you can say like 1 or 0. Okay. And x1 bar is just the opposite of x1. Okay, so we have these Boolean literals, and you can see that we have these bracket things. So the 3 in 3 CNF SAT represents the maximum number of literals in a bracket. So that is 3, see 3, 3 and 3. Okay, and the CNF is a special form in which all the brackets are joined with ANDs, and inside a bracket you can only have ORs. See? Okay, so your goal is to come up with an assignment for all the values like x1, x2, x3, so that this entire equation gives you true. Notice that it is all the clauses are joined by bunch of ANDs. Okay, so you need to satisfy each of the clauses individually. This needs to be true, this needs to be true, this needs to be true, this needs to be true. Then only it will result to a true. Okay, so but you don't need to make each literal also true. So maybe this is true, maybe this is false. One true is good enough for you to satisfy the whole clause. Okay, but in order to get the entire equation as true, you need to satisfy each clause. Okay, so this is the 3 CNF SAT problem. So now I given a 3 CNF SAT problem, I want to reduce it to a subset sum problem, which sounds pretty insane, because from this weird equation, I want you to find a set of numbers and a target value, which is pretty weird. This has literals and equations, and I want you to find a set of numbers and a target value. So hang on with me for the next 10 minutes, and the operations which I would do wouldn't make any sense, and when I'm done, it'll start making sense. So the next 5 minutes would be quite weird. So let us try to derive the set of numbers and a target value from this 3 CNF SAT equation. Okay, so this is the same 3 CNF SAT equation. So I've written all the literals in the as the column headings and all the clauses. So this equation had three literals, x1, x2, and x3, and four clauses, c1, c2, c3, and c4. Okay, and for each of these, for x1 I'll make two variables, v1 and v1 dash. For x2 I'll make two variables, v2 and v2 dash. For x3 I'll make two variables. Likewise, for c1 I'll make two variables, s1 and s1 dash. For c2 I'll make two variables. For c3 I'll make two variables. For c4 I'll make two variables. Okay, and if you see the first block here, okay, if you say this, you'll see that v1 represents, okay, v1 represents x1 being true, and v1 dash represents x1 being false. So similarly, v2 represents x2 being true, v2 dash represents x2 being false. And similarly, v3 represents x3 being true, and v3 dash represents x3 being false. Okay, you would notice that I put everything else as 0. 0, 0, 0, 0, 0, 0. Everything else is 0. Even everything here is 0. Everything is 0. Okay. Let me clean this up. Yeah. Now, if you concentrate on this block, you will see that for C1 and S1 and S1 dash, I put 1 and 2 here, 1 and 2 here, 1 and 2 here, 1 and 2 here, and rest all the places I put 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, I'm doing this without any logic for now. Okay, and so now we are left with just this the upper right block. Okay, now let me see. So v1 represented x1 being true. So in the first row here, we'll fill thing as follows. So if x1 is true, we'll put 1 at the places of the clauses which are satisfied by x1 being true. So if x1 is true, clause 1 and clause 4 are satisfied, and clause 2 and clause 3 are not satisfied. So we can write 1 here and 1 here and 0 and 0 here. So likewise, v1 dash represents the clause x1 being false. v1 dash represents x1 being false. x1. Okay, so this means if x1 is false, we have to identify the clauses which are satisfied, and they are these two. So these two are satisfied when x1 is false, so we'll put zeros at these places. So for the next row, we need to find the clauses which are satisfied when x2 is true, and those are, only the last clause, this one. So this one here, and this thing is 0, 0, and 0. And likewise, so we have to find the clauses which are satisfied when x2 is false, and these are clause 1, clause 2, and clause 3. Clause 4 is not satisfied when x2 is false. So now we want to identify the clauses which are satisfied when x3 is true, and these are these. So, and likewise we'll fill for these. Yeah. Okay. So, and the last row we fill as just 1, 1, 1 at the literal place, and 4, 4, 4 at the clause place. Now I claim that my target value is 1, 1, 1, 4, 4, 4, 4, and my set of numbers are, all these numbers, like this, all the rows, form a number for me. They're not Boolean numbers, they're like in decimal. Okay, so all of them form a number for me. So by that I mean, like, let me write from bottom to up. So these are like 2, 1, it's like 2, 1, and then 20 and 10, 20, 10, and then 200, 100, 2000, 1000, then 11100, then 10011, and so many more. Okay, so you see we have like, if you see this entire thing, we have 14 numbers. So now I say that I have identified as equivalent subset sum problem, which has the target value as this and the set of numbers as this. Okay. Um, so I've done a weird reduction here, but this might not be true. So we need to verify if the reduction is a right reduction, and with that I mean, so the for a reduction to be valid, we need to satisfy this constraint. So if the subset sum has a solution, then the 3 CNF set must have a solution, and if it doesn't have a solution, then this cannot have the solution, no matter what. Okay, it's same as saying, if 3 CNF set has a solution, if and only if the equivalent subset sum has a solution, and this like, so if and only if makes it vice versa also. Let us see how that works and how is that true. Okay. For the as the first step, let us assume that the 3 CNF set has a solution. Okay, so by that I mean this must be an assignment. Okay, an assignment like x1, x2, and x3. Let's say this is true and false and true. Yeah. So this is a valid assignment. So not only I am making a claim that 3 CNF set has a solution, I am also providing a solution for that. Okay, and you can check that this works, and this is this indeed makes the entire equation true. Okay, so now I say that if this 3 CNF set has a solution, then the equivalent subset sum will have the solution. And I'll not only show that the equivalent subset sum has a solution, I'll find you the solution for you, knowing this assignment. Okay. Let's say, so we want to select the rows which represent x1 being true, x2 being false, and x3 being true. And those are these rows. So this represents x1 being true, this represents x2 being false, and this represents x3 being true. So I mean, I so far in my subset I've selected these 3 rows, like 1 0 0 1 0 0 0 1, and then 1 0 1 1 1 0, and maybe 1 0 0 1 1. Okay, so far. Okay, now you would see that if the 3 CNF set has a valid solution, x1 is either true or false. It's not both. It cannot be both. So you can never select both v1 and v1 dash. Likewise, you can never select v2 and v2 dash. So because that would say that if you select both vi and vi dash, that would say that xi is both true and false. That cannot happen with a valid assignment for the 3 CNF set. So that means if I say that the 3 CNF set has a valid solution, that means x1 is all the xi's are either true or false. So that means we will never select consecutive like 2 ones. Okay, so this will help us to restrict the target, and we will match the first part of target, and it will always be 1 and never be 2. Okay, now since I said that the 3 CNF set has a solution, that means all the clauses must have been satisfied individually. Okay, so with this assignment, the green rows represent my assignment. Okay, and and this was our assignment. X1 being true and x2 being false, and x3 being true. So that means this assignment must have satisfied each of the clauses. Okay, note that if x1 is true and x2 is false, if so, this clause is satisfied by two of these literals. Okay, but we don't need all the literals to satisfy a clause. Uh, Even one literal being true is enough for a clause to be true. Okay, so in this case, we see that with our assignment here, uh, we notice that the with our assignment the clause C1 was satisfied at two places. Well, that's fine. So this so if I add up all the things in the column C1, I already get 2. Okay, but we see that we have to match the target value of 4. Okay, so that means we can take one helper variable here, and that will add 2 more, and we can reach the target variable. Okay. Okay. Notice that if we didn't have anyone's in the column, in if we didn't have anyone's for our C1 column with the assignment, then no matter how many helpers variable you would have taken, you could have only reached 3. Okay, so if the clause was not satisfied, no matter how many helper values you would take, you can only reach 3, and you can never make it to 4. Okay, so you need each of the clauses to be satisfied by at least one literals. Okay, so so the columns here will sum to either 1, 2, or 3. But if they sum to 0, that means they were not satisfied by any of the literals. That means no matter how many helper variables you take, you cannot make it reach 4. Okay. Okay. So now let us see the column C2. Let us see the column C2. Okay, and we see that C2 is satisfied by this, by x2 being false. Okay, and that gives it 1. So we would need both the helper variables. You need both the helper variables to make it 4. Okay, now let us see C3, and we notice that C3 is satisfied by x2 being false and x3 being true. Okay, and that gives it 2. So we need to use only one helper variables to make it 4. Okay, if we see C4, we see that was satisfied by x1 being true and x3 being false. Oh, sorry, x3 being true. Okay, so we get 2 already. So so we need to select just one helper variable to make it 4. So now I say that out of all the rows that form my subset of numbers, if I select just the green rows, so that would be my S dash that adds to the target variable. Okay. So you can see if we didn't have if the assignment of x1, x2, x3 didn't satisfy the SAT formula, that means at least one of the clauses were not satisfied by any of the assignment. That means you would not get any ones here. Okay, so it would be all zeros. Okay, so no matter after that, no matter how hard you try, you can only add it to 3, and you can not make it till 4. So you need with the assignment, you need to satisfy all the clauses by at least one literal. Okay, So if you want to see the other way around, let us assume that the subset sum has a valid solution. Okay, that means you were able to make it 1114444. So if you concentrate on the first part 111, that means you are either selecting v1 or v1 dash, or v2 or v2 dash, or v3 and v3 dash. And so that means for all the variables x1, x2, and x3, you are either selecting true or false. Okay, so this part is satisfied for the SAT problem. Okay, now since I said that we have the solution for the subset sum problem, that means we were able to find a subset of numbers which were adding up to 4444. That means no matter what we would have taken from the helper variables, we would have relied on at least one from each of the columns till here. Okay, and that can only happen when like our selected columns gave at least one, and that means our selected columns or the selected assignment satisfied each of the clauses. Okay, so if either at least one of the clause was not satisfied, we can never make it 4444. So if we had the solution for the subset sum problem, that means uh, uh, we must have satisfied all the clause with the assignment, and then only we can make it 4444. We would have borrowed at least one from the top column till here. Okay, so yeah, this completes the intuitive argument for the proof. So this was not intended to be very formal, and hope this helps. Uh, thanks a lot for watching.